session, we get so many participants from different countries. So we also get some. So that's why we attach so many different time zones in our schedule. So yep. Okay. Before we begin, I would like to introduce myself. My name is Wiratama. I've been in simulation, especially CFD, for more than 10 years in 2013. And my last education is from master degree in mechanical engineering from New York University. So yeah, my perspective may be mostly are from mechanical engineering. But in this discussion, I would like to make the discussion more general. So if you are architect or maybe civil engineers who design HVAC design, uh, I will make the material not too mechanical. Okay. Uh, before I before we deeper about the ASHRAE standards and the design, I would like to discuss a little bit about the physics or maybe the science behind the thermal comfort. So, let's say we have a room. We set the HVAC temperature to 22 degrees Celsius, let's say, and we have a chair with steel and also leather material. If I ask you which temperature is lower, it is metal or it is leather, maybe most of you will say that the metal has lower temperature because if you touch the metal, you will feel colder. But that's not actually true. The temperature is actually the same because the chair doesn't generate or absorb energy or so the temperature both are 22, but why they are different because they absorb different heat flux or heat transfer rate. So that's what I want trying to say is that human body actually feels the hot or cold not based only on temperature but basically on the heat transfer. So this is how human body actually react to temperature or regulate the temperature, or we also know this as the thermoregulation, which is the regulation of our body to adapt the temperature or the like the climate. So if we get thermal radiation or thermal heat source, our brain will tell us to get some, seeking in the shade, let's say, or maybe change our clothes to the more lightweight or consume more water. That will change our behavior. But unconsciously or physiologically, our skin will also react by dissipating heat via evaporation. So if we sweating, it just actually release the fluid that the fluid evaporates, and during that evaporations, the will absorb the latent heat via that phase change, which makes our skin feels colder because of that heat transfer. It is the same phenomena like if you go to the a swimming pool and you go outside the swimming pool, you will feel colder because of that evaporation. Temperature is the same, but you feel colder because of that evaporation. And our body also uh, exchange heat through the dissipation of a radiation and also conduction if we touch the floor, let's say, or maybe touch the wall. So the heat transfer actually uh, consists of different phenomena here, not just simply temperature. And the human body temperature distribution itself is not uniform. Let's say if our temperature is 37, it doesn't mean that our body will have the same temperature. Let's say if we are in the room with 30-degree ambient temperature, the gradient will mostly uniform. But if we are in the 20-degree ambient temperature room, we will feel different high temperature gradient, which is also will affect our comfort level. So our brain will tell this high gradient as not as uncomfortable situation, which we will discuss later. The point is the human body itself doesn't have a uniform temperature, so it will change the way we interact with the HVAC design or the room temperature. And okay, let's discuss what makes the different in order to design the comfort to our room. First is clothing, or in ASHRAE 55 we will know the parameter as CLO. So the value of one is you know is corresponds to the winter clothing. If we use like multi-layered clothing, which is very warm, we consider that as 1 CLO. If we use like lighter summer clothing, we use like 0.5 CLO. This is related to the evaporation rate. If we use the multi-layered clothing, of course the evaporation rate will be slower, and the conduction of our body to our radiation to the environment will be also slower. And if you purchase the ASHRAE 55, you can actually get this very concise list of CLO numbers, like the trousers, short sleeve shirt, and anything else. Sweatpants, a long sleeve sweatshirt, and many more. And yeah, of course, you have to keep update with this standard, because we know that standards is keep updating, and maybe the value in these slides will be different, yeah, every version. Okay, the second thing that we have to understand is the metabolic rate. So basically, if we have more activity, like if let's say if we sit, of course the temperature or the heat flux will be lower compared if we are like sitting while typing. Or maybe if we do the exercise or maybe running, it will dissipate heats like 4 to 8 more heats to the environment, which will in turn increase the room temperature. And again, you can get the full list of this MET. We call this metabolic rate the MET, the detailed list in the ASHRAE 55 document. And that's the second one. And the third one is the humidity. We know we have the relative humidity and we have absolute humidity. And here, what I mean by humidity is the relative humidity. I don't want to talk the detail about, the how to calculate them, but humidity is basically tells us the contain the water contained in or maybe the in the room. Let's say if we in the humid room with moisture content, high moisture content in that room, our body will less likely to evaporate, because the the sweat will be saturated relative to the room humidity. That's why we feel uncomfortable, because we cannot dissipate the heat via evaporation. On the other hand, if the humidity is too low, or we have low moisture content in the room, it will make our eyes or our nose feels really dry, which is not also makes us uncomfortable. And maybe in other standards that I will not discuss here, or this humidity will also affect another uh, consideration like the airborne virus or maybe the fungal or bacterial growth or maybe even the moisture damage to our furniture if the humidity is too high. But I don't know. I don't think it is covered in the ASHRAE 55. Okay, this is humidity. And yeah, again, the point that you have to understand is that the humidity will affect the evaporation rate from our body to the environment, which in turn affect the thermal comfort. And the other thing that we also have to consider is the local thermal discomfort. So not just design in the, you know, in the room as a whole or averagely uh, design the, like the calculate in the average value. We also have to consider like the local condition of the occupants. First one is the draft. Some reference use draft, DREFT. Some other use like draft. This is basically tells you how fast or how how wind affect our body locally. If we, let's say, nearby the fan or maybe in maybe in a beach, let's say, we will get some high draft with even if proper temperature and humidity, but if the draft is too high in our body, it will feel uncomfortable. And secondly, the asymmetry. Asymmetry can also creates discomfort, whether it is like horizontally or vertically. Let's say we if we have like radiation, if let's say we are in cold outside temperature and we use the we use fire to warm up our body, but just our front body get the radiation, but our back feels cold. It will also create the discomfort due to the asymmetry. This is also true for the vertical different air temperature difference. If not mistaken, it is recommended to not make the gradient more than like 3 degree Celsius. So yeah, so we have to make sure that the temperature gradient is not high. And floor temperature is also affect our comfort level. Let's say if we have proper room temperature, but we cannot use our shoes in that room and we step on a very cold floor, of course, it will also makes us discomfort. Okay, let's define another parameter called the mean radiator temperature. This is actually the temperature that represents the surrounding heat transfers, like the from the ceiling radiation or maybe radiator radiation, or maybe our heat dissipation to the cold window, let's say. So the temperature of our body, like we measure using the thermometer, is will not be the same as we feel because we have some other external factors. And this temperature also called the mean radiation temperature. Okay, let's talk about the how ASHRAE 55 define comfort. So actually, or essentially, ASHRAE 55 is standard to define the thermal environment condition for human occupancy. So it is widely used to for indoor uh, room design or maybe a building design for comfort or thermal comfort. So it will not discuss detailed about the virus spread or maybe the bacterial growth. It will that will be discussed in another standards. So the first parameter that defined by the ASHRAE 55. It is actually not only for ASHRAE. This parameter also used in other standards like the ISO 7730 is the predicted mean vote, which is basically combination of metabolic rate, clothing insulation, air temperature, air velocity, like we discussed previously, and the mean radiant temperature. That's why I introduced you this mean radiant temperature and the relative humidity. All of these parameters are, like converted into a single parameters, or single, yeah, parameters with quite long equations. So I will not display it here. And that basically tells us how the occupants feels in that room. So it is like if with the total calculation is zero, we will feel that uh, the room is quite natural or comfort. But if the value is more than zero, like 0.5 or 1, it will be warmer. Or if it is negative value, it will tells us that the temperature is cold. So of course we want to design the PMV is to be zero. And yeah, of course we cannot achieve of zero value everywhere. So ASHRAE 55 define or like suggest the value in the range between minus 0.5 to 0.5. So yeah, I will tell you how to calculate this later. But this is the idea. We get some parameters, actually six parameters to be included in this calculation to get these values. Okay, this is PMV, one of the fundamental parameter that we use in ASHRAE 55. Then the second one is PPD, or predicted percentage dissatisfied. This tells us, let's say, for example, we have 100 occupants in a building. If we ask them, are you comfortable in this room? If they say they are not comfortable, all of them, like 100 people say they don't satisfied, the value of PPD will be 100%. If we change again the temperature, the humidity, and we ask again the same question, and maybe just 10 people said that they are discomfort and the others said comfort, so we can say that the PPD is like 10%. So it is basically like statistically speaking, uh, you know, statistically comfortable based on the occupants. And this is can be calculated from the PMV value by using this simple equation. Not really simple actually, but we can easily calculate how many percent of the occupant will be uncomfortable statistically. And again, the lower the value will be better. Then ASHRAE 55 suggests us to use this 10% value. Again, the value of this PMV and also PPD, the 0.5 and 10% is based on the latest standard, but you have to read again if any update in that standard. So maybe this value can be changed, during the time. But the idea is still the same. Okay, this is PMV and PPD. Basically, has a very long equations. If you purchase the standard, you will get like online calculator or maybe the code that you can copy and paste to calculate these values. Okay, the next parameter is the draft rate, and the draft rate is again like we discussed previously, is how the air interact with our body. The faster the speed, locally in our body indicates the higher draft rate. So the suggested draft rate is around 30. But this is not explicitly stated in the ASHRAE 55. I think I think it is more used more in ASHRAE 7730. But yeah, we still can use this parameter also. This is the draft rate. Okay, if we open the document of the ASHRAE 55, we can get some charts that relates some parameters like the average airspeed and operative temperature. Operative temperature is essentially how we feels like in that room or in that environment. It is the combination of the mean radiant temperature and also dry bulb temperature. Actually, if we check the weather application and we see the feels like, it is actually the operative temperature, which have complex equations related to the humidity and anything else. Okay, but here we can see we not only consider only temperature, we also consider the speed, temperature. Here is the clothing, and here is the PMV. We can see the value from 0.5 to 0 minus 0.5 to 0.5 in these lines. So we have to make sure that our design is within that operational range to make sure that our building is compliant with the standards. Or maybe not only design, we can also, from the existing building, we can measure this airspeed, temperature, humidity, and we can plug this to this chart in order to, check whether the design is comply or not. And this is traditionally done using online calculator. You can access this. I think it is actually freely available on the Google, on the internet. You can just type ASHRAE 55 calculator and you can find this free calculator. You simply input the operative temperature, airspeed, relative humidity, and metabolic rate and clothing level, and you will get the operating condition if it is within the range of that you know uh you know like the comfortable level, it will complies with ASHRAE standards. If it's not, let's say the temperature too high or temperature too low or maybe the humidity too high, and if it is outside this green region, it will not comply with the ASHRAE. But the problem is we sometimes, or maybe if we design a building, if we use the equations like the cooling load or maybe the heat transfer from the ceiling for the floor or the total number of occupants, they are all just like the average value of that room. So we cannot actually see the detailed temperature in that table or in that corner, or like we cannot actually uh, see the detail. And maybe one point in that room comply the ASHRAE 55, but another place, maybe in the another, if if we see this model, let's say, if we see this image, let's say, maybe we can get very different result between this table and this table in the same room, which is problematic to our design. This is also will be a problem related to some local discomfort we discussed earlier. Let's say for the thermal stratification, this is basically like temperature stratification, which is the vertical variation of the temperature. Let's say in average, we design the temperature to be 22 degrees Celsius, but because we use like low, because we know that the cold air has a lower density, which will be going down to our feet, which make our feet colder, but the upper temperature will be higher. That will be also make a new another problem, which we cannot detect easily with the traditional calculation. And yeah, this is the relationship between the PBD percentage predicted percentage dissatisfied with the temperature differential. The higher the surface temperature differential, the higher also the predicted the PBD. Yeah, again, that's the problem. We cannot easily calculate in the design process, using just like average value of the CFM or maybe the cooling load. We cannot reveal some detailed gradients. That's why some engineers using a tool called the computational fluid dynamics or CFD. You don't have to be intimidated by this complex equation, but this is this method is actually quite mature in the industry, especially for mechanical engineering design or maybe civil engineering. But yeah, I don't want to discuss that uh, the detail, but the point is the method is actually calculate or simulate the actual geometry you designed maybe on Revit or maybe on SolidWorks or Autodesk Inventor with some complex equations and some complex numerical method generates the plot of pressure, temperature, humidity, which in turn can helps you to see the detail of the room parameters and at which in turn again will help you to calculate like the PMV, PPD, and anything else. This is very helpful. But the problem with CFD software is mostly too complicated to be used by non-CFD expert. So because it is use some complex equations, some partial differential vectors, complex equations, in the operational of the CFD itself, you have to understand what is the best method to be used to prevent the, like to reduce the error or maybe even to um, to make your simulation not blow up with some random inputs. And the second one is too costly to buy the non-utilized feature because most of the CFD packages are basically general purpose. So if you buy CFD software packages, you can use that for HVAC. With the same product, you can also simulate aerospace, like lift and drag. You also can simulate electronic coolings, or maybe you can also simulate the high-speed rotating turbo machineries. So yeah, that's what makes these CFD packages not ideal to be used for like if you are like architect or maybe the person that who don't want to bother a lot about the CFD simulation. And those capabilities also comes with the high price. So if you buy the CFD packages, it will be you have to pay not only for the HVAC simulation, but you have to pay the other capabilities that makes the CFD products so expensive, which makes it not not feasible for you if you are like the independent consultant or maybe just have seasonal project like design a house with with only 1 month's simulation, so you don't have to you know the price and the procurement process is just not feasible to your whole workflow. Okay, this is what I said previously. If you want to simulate the combustion or maybe the turbo machine analysis, it will be the same software to solve like aerodynamics of a cat, let's say. So yeah, that will be so costly. I mean, it is costly for you if you just want to design HVAC, but if you are a huge company who want to invest deeply for your R&D, you know, serious aerodynamics problem for automotive or maybe aerospace, it will be worth it. But for just design a building, which maybe takes like 1 week simulation, it will be too costly for you. And the general purpose CFD is mostly make extra works to analyze like PMV or PPD. They are generally not included in the package, so you have to do extra works, let's say, coding your own equations inside to calculate PPD, which we know the equation will be so long. And yeah, if you are not expert maybe in coding, that will be another problem. And this is maybe the most challenging problem in safety, which is meshing. So if you are architect or maybe civil engineer that not familiar with parametric 3D software like SolidWorks or Inventor, maybe you use CATIA. I mean, if you use Revit or maybe SketchUp, most of the time the design will be uh, in the surface model or STL, and they are very dirty to be simulated in CFD software, which makes the CFD simulation not an option for the uh, this kind of geometry. Because yeah, let's say you are designing a very complicated building and you want to simulate, you have to give the geometry to mechanical engineer and rebuild that in SolidWorks and export again, which takes a lot of times and efforts. Okay, that's why in this webinar I would like to introduce you to the Tensor HVAC Pro, which will tackle this kind of problems. So we have software that dedicated only for HVAC, flow, and thermal simulation. And the software is designed to be highly intuitive, easy to use, not for CFD expert, but if you are, again, civil engineer or maybe architecture or maybe you are mechanical engineer, but not really have experience in CFD, but you just want to design HVAC, the software is designed for you. Okay, the first feature that we want to emphasize in this software is the software the software itself is very compatible with existing surface modeler like the SketchUp or maybe Revit, Rhino, which are commonly used in architecture and engineering design and construction and engineering. So you don't have to worry about converting the geometry to solid models in SolidWorks or Inventor. You just simply export directly from SketchUp or Revit in STL format. And of course, if you are using SolidWorks, CATIA, Inventors, they can also easily export the format to STL format. And the software also designed to be simply and straightforward as possible. So here you can just simply define the units or maybe the temperature, the velocity, so you don't have to understand the detailed physics behind it. Just so you don't have to worry about the selecting the turbulent model, let's say, or maybe the numerical methods that makes your life easier and more focused on solving the HVAC problem instead of solving the numerical problems. And the mesh is basically one of CFD, you know, steps that you have to go through before you get the simulation. And for this Tensor HVAC Pro, you can easily mesh some detailed geometries like this flower, let's say, or maybe these books or this furniture easily. And if you are safety user, maybe you will, you know, understand how hard to simulate this kind of geometries. Okay, and of course, because it is dedicated to CFD, I mean HVAC simulation, the results will also display some important parameters like the velocity, temperature, PMV, PPD, the air, that is highly important to comply with the ASHRAE 55 standards. So you don't have to worry about, converting those values from humidity, velocity, temperature, and manually code your calculators to find the PPD and PMV. The software will do it for you. And the best part is the price is only 800 USD annually. And if you want to buy like 3 years, the price is around 2000 US dollar. And yeah, you can also lease it in a monthly basis. So you can buy like only $80. So yeah, we know that HVAC project is mostly done like 1 month or 2 months. So you don't have to, you know, purchase the whole perpetual license. Okay, let's do a simple demo. So in this demo, I would like to make a simple simulation. Let me share my screen. Okay, so this is basically the user interface of the Tensor HVAC Pro. We just released the version 2026 1.2. You can also check our pre-version in our website at tensorcfd.com. Okay, let's create a new project. We will simulate basically a cafe. So it is like a cafe area to, with two occupants and one worker there. Let's save the project in our browser. Oh yeah, in this version 2026 1.2, also available on the Mac. So if you are a Mac user, you can run natively in your MacBook because we know that most architects are using MacBooks. So yeah, we don't just design it for Windows user. Okay, let's import the geometry. Uh, let's use. I already prepared the geometry. You can also use this geometry. I will share you this geometries later. Okay, here we can see we have some models. We have workers here who works behind the bar, and we have two occupants, and we have one air conditioning unit. Of course, it is not ideal. It is just for demonstration purpose. Okay, let's define the definition of these, uh, you know, uh, models. For the bar, I will define it as the wall. So we have some parameters here. So the inlet is basically the place like blow your air, can be this inlet, and the outlet is where the air is sucked back to the system. Let's say here, or maybe if you are using diffuser, it will be the inlet, and the object is basically yeah, like human or maybe a chair or maybe desk that will be meshed more, like finer compared to the wall. So object and the wall are basically the same, but object will have a finer mesh. Okay, the bar is object, bench object, and ceiling is wall because we don't have to worry about the resolution of the ceiling. Chair is object, chair two also object, coffee maker is object. Here we have coffee maker. And the floor is wall. Human sitting is object. We wanna have a better resolution around there. Indoor unit is actually this one. Indoor unit will be object and the wall of course is wall. Okay, now we want to separate the inlet and the outlet. So basically, if we are using SolidWorks or maybe some geometry editor, we cannot separate its surface in, like from this 3D object. So here we can separate them by just simply click uh, this object and name it inlet, let's say. And for the top part, I will define it as outlet. Okay, uh, of course, we will define the inlet as inlet and outlet as outlet. Okay, here we go. And yeah, if you notice here, we don't have to worry about, to convert this geometry into negative domain, like the traditional CFD, when we have to, convert the geometry to the negative object, we just simply define the wall with its thickness and the object with its, presence without, as a positive objects. And here for the mesh, we just leave it as it is. We use medium or fine if you want a finer result. But, using finer mesh will makes your computational effort higher. But yeah, it comes with better resolution. But if you want to check your wireframe, you will just simply use this wireframe and you can, check the resolution before you actually run the meshing. Okay, let's update the mesh. It will take a couple of minutes, depends on your resolution. And yeah, you can also use the manual resolution here if you want. Just input some value you want. The value here are in meters. And yeah, you can also check here with this roller to make sure that your geometry is exported with the correct units. And if wasn't um, if it wasn't correct, you can also scale or maybe translate with these tools. Okay, we are done with the mesh. You can check it with ParaView if you like, but it is not mandatory. It's just like to make sure that your mesh is, you know, correct. Oh, I think we lost our human here. Oh yeah, yeah. I think I forget to check this one, but okay, let's just skip this because will not run it directly. I already run the finished project, but yeah, you get the idea how to just ignore some object here to generate the mesh that is not, uh, you know, yeah, basically just how to ignore the objects. Okay, let's go to the boundary. Here I want to make this indoor unit. blow the air in the, Z direction. Here we can see the coordinates here. Or if you like, you can make some angle with the Z and minus Y, let's say. But here I just want to give it like 0.5. Yeah, you can check the value of this velocity maybe from your supplier of this air conditioner, or maybe you can use the uh, available data. We also have um, unit converters here. If you're not comfortable with SI unit, maybe you are in the US. And for the temperature also you have like Fahrenheit. Kelvin actually is not commonly used in HVAC, but the code is basically in Kelvin, so I also add it here. Okay, for the other parameters here, for the object, let's say human, as we discussed previously, also dissipates heats based on the metabolic rate. So we can change the temperature, let's say T is for temperature. If we have constant temperature for human body, you can input that. Or if you want more accurate result or more realistic result, you can use this gradient temperature, which is basically defined by heat flux. If you don't know the values, you can just simply click here to see the reference. Here you get some, background theories, the equations. Yeah, this is the most important thing. So the human sitting will be have around a heat flux around these values like we discussed before with the MAT, and this is the K value to calculate. So we just basically maybe it's like this one or maybe 160, or yeah, depends on your design. And this is also the same thing for human sitting and for human standing. Let's say we give a higher value. Let's say the worker is doing like, mixing stuff. So the heat dissipation is higher. I don't know, you just put some random values. You can have a better value than me if you are, more experienced in this calculation. Okay, for the wall, I will also input some heat flux value. Here we also have some reference here for the internal wall. Concrete, we have like 19. Of course, it will change depends on the weather outside. Let's say if you are in the winter or maybe in the summer, of course this value will be different. And for the floor, it will be the so driven is basically we don't define the temperature or the heat flux, so it will be affected directly by the environment. Let's say the environment has the 30 degrees Celsius, so the floor will be also 30 degrees. So this is the ceiling. Oh, sorry. I think this one is the wall and this is the ceiling. The ceiling is, let's say 30. I don't know. We just like put some random numbers. Okay, just update the boundary conditions. Next, we go to the general setting. Here you defines the parameters that we've been discussed previously, like the clothing. So let's say the people sitting in a cafe using, summer clothing. So we just use 0.5. Except you want to design, like a gym center, let's say, with or people working out inside that. Of course, you will have another clothing and also the metabolic inputs. And this is the relative humidity. It will be highly depends on the countries. Let's say if you are designed in Asia or maybe in Europe, of course, this value will be different. Okay, the last thing will be the solver setup. So this will determine how many times steps you will need to solve this simulation. So the higher the value will makes your simulation more converts or better. In this simulation, I will just use 5,000. And this is the number of cores. It depends on your hardware. So if you have better hardware, the simulation will be faster with the more cores running. And don't forget to update the setting, and we can start running. This running takes around 30 minutes or 50 minutes. I don't really remember, but maybe I don't want to wait until it finishes because it is like 1 hour session. The 30-minute running will be waste our time. So I just want to show you how it runs. So when we simulate, we will get some curve like this. So if the value is lower, or maybe like doesn't change along with the iteration, it means that your simulation is okay. I just want to stop this running so we don't waste our time waiting this simulation. Let me just open my finished running case here. Here we go. It takes around 5,000 iterations, and yeah, let us check the results in ParaView. Here we go. So let's check the values inside this cafe by first make this color solid so I can make it in wireframe. Here we go. We have 2 person sitting now. um, in this ParaView, actually the temperature is still in Kelvin, so I want to make it in Celsius by using this calculator. Of course, I will publish another detailed video about the tutorials and the how to use this ParaView. So I don't want to get detailed in this. So let's say this is the temperature in Celsius, which is temperature minus 273 Kelvin, point, I don't know, 0.5 or something. Just use this one. Okay. Um, let's see what's happening inside this building. Let me first make a slice here. So the slice is basically just slicing the building and tells us what's happening inside the building. Okay, from the temperature. Oh, this is still time 100. Let's go to the last time, which is 10,000. Here we go. We get our temperature, or we can slice in a better place when the human sits there. Here we go. And we can make another slice. Wait a minute. Oops. Oh yeah, here we go. I think okay. Okay, here we go. Let's make another slice for the horizontal distribution in the y-axis here. Oops. Okay, it's fine. And yeah, we can see the detailed temperature here. We know that this person feels colder because it's nearby the AC. Of course, it's not ideal. I just want to make some extreme case. And let's see the other parameters. Let's like we discussed previously, the DDR, the draft rate, the PMV, PBD. Let's check one by one. The draft rate is quite high around this person. The limit is 30, so we still have 31, which is not, which is okay because the 31 is around here, so people feel here like 25. But I don't think it is good also because we know from this value, 25 is, yeah, not really okay, just intermediate. Okay, let's check another parameters, which is PMV. Here we see that the distribution is from minus 0.23 to 0.6, which is beyond the ASHRAE 55, but don't worry, it is just like automatically generate. So let's change our range to ASHRAE standards, which is 0.5 to 0.5. I mean, minus 0.5 to 0.5. Here we go. We actually get a good result around the worker and the second occupant, but oh yeah, unfortunately we don't satisfy these occupants. That's why we have to evaluate the placement of this AC unit, for example. Okay, let's check the PPD or percentage dissatisfied value, which is from 0 to 5 to 89%. Let me change again the range from 0 to 10% because ASHRAE suggests us not to make the design more than 10%. Again, we satisfied the design around this person and the second occupant, but here we see that the person is not quite satisfied with this design. And maybe you don't have to worry about the ceiling. Let's say the ceiling have higher PPD, but again, we don't think the occupants will be on the ceiling. Okay, this is PPD. Let's check another result. Temperature, we already checked that. The velocity, I think for ASHRAE 55, it also constrains the value of velocity. You can check. It is in, I don't know, it's like 30 or 40 feet per minute or something. But yeah, I think the result will be almost the same as the DR value, almost the same distribution. And we have some extra data here. The air age is basically how long the air already there in the room. Let me check. Let me change the distribution here. Oops. Oops. Let me make it. Well, I don't know. Just make it. Okay. So here we can see that the value of the edge of the air will be higher around this person because the circulating air will further away from this person, so it will also creates maybe not discomfort, maybe it will change maybe the odor or maybe the virus spread or anything else you can also analyze with this software. Okay, that's how the Tensor FEAC Pro or the design software can actually helps you to comply with the ASHRAE 55 standards. So you don't have to wait until your building um, done, like built, and you can scan them and you find the problem, but you can, find in the very, very early of the design process from your Revit or your SketchUp. Just simply import here, and yeah, you can simply check the PPD, PMV, But of course, it is just like simplified version of the analysis. You have to consider about the weather, let's say in the winter, of course, the simulation result will be different, maybe for the summer, or maybe morning and also night. I will also have different value of like thermal radiation. But yeah, I think you get the idea. These are the values that we've discussed previously. And the point of this simulation is actually to reveal the how this air conditioning or maybe diffusers uh, placement will affect the distribution of the PMV, PPD, and anything else. So you can just simply move the the units or maybe change the diffuser types, let's say, and you just can simply run the simulation in like 15 or 30 minutes to get the different result before you actually can build the building. Yeah, that will saves a lot of you know revision costs and also rebuilding, even rebuilding cost, if you design that like realize the problem after the building done. Okay, it's already 1 hour, so maybe the last thing that I want to say, if you want to try our version, I mean our software, you can check it on the tensorhvac.com/free version, and yeah, you can do some basic simulations with some limitation. It is just for one wall, one object, and one inlet and one outlet. So it's just like for trial. And yeah, it is free. Please don't use it for commercial purpose. And yeah, that's all for me. It's already more than 1 hour. And if you have a question, please raise your hand, or maybe you can contact me via email at Viratama. Let me type it on chat so you can ask some question. And yeah, after this session, we will upload the record of this webinar, so don't worry. We will email you for the record. Okay, if there's no question, thank you for all for joining this webinar, and I hope we can meet again in the next webinar in the next month.
Sir, how are
And
you?
oh yeah, sure. You wanna
Uh,
ask a question?
yes, sir. Sir, I am a final year mechanical engineering student from Pakistan,
Mhm.
and sir, I use many CFD simulation softwares like ANSYS, COMSOL, Multiphysics, Abacus, and specially dedicated HVAC softwares like Siemens Design CC and uh, Sky Spark, and they
Mm.
provide similar features like Tensor HVAC Pro. And what makes it different from others?
Oh, I see. So the first, of course, is the price. I think the Siemens, like, I don't know. I don't want to spill the price in this open webinar, but as far as I know, the price of like below the 800 USD is nothing like this in the market, first. And secondly, we design not only massless capabilities like the other dedicated HVAC, like from Hexagon, maybe ANSYS also have, I don't know. I don't think it's HVAC, it's for like electronic cooling. They are using uh, solid 3D model, like the Parasolid or maybe the STL, I mean, sorry, or maybe the STP or maybe I guess. So if you want to use STL directly, it will be quite hard to use. I don't know. Maybe it is impossible. I never tried the Siemens one, but for the other software like ANSYS Fluent or maybe SolidWorks, you cannot import STL. that's a huge problem because if we are HVAC designer like architect or maybe civil engineer using Revit or SketchUp, you have to, reconstruct the whole building from the beginning. And maybe the other thing that you will, uh, find is the robustness of the mesh and also the computational setup. So the Tensor HVAC Flow Pro is basically designed to automatically select for you under the hood. I mean, you don't have to click the turbulent model, or maybe you don't have to change the mesh type. You just simply import the geometry and the software will select it for you. Maybe for mechanical engineer it is less, you know, flexible, but for daily case in real world application, you don't have time to, select the turbulent models or, some simple piso, yeah, anything like that. I hope that answers your question.
Yes, sir. Thank you. Thank you very much.
Okay, maybe another questions.
Hai, Pak Kaisar. Can you hear me, Pak?
Hi. Yeah,
Yeah.
sure, Pak Anjas,
Eh,
please.
Let me introduce. My name is Anjas Nurhidayat. So actually, currently I'm status with working in data center,
Hmm.
but my background is more to like a quality observation for the project construction. But
Hmm.
I want to know, beside insight from the design engineering, regarding the 3D flow in applying 3D flow and thermal simulation to meet ASHRAE comfort standard. To what extent can this simulation result represent actual condition in the file? So, what the limitation like or assumption should engineer consider when using the tool as basis for design?
Okay, very good
Mm,
question. First of all, data center, that's a very, hype lately.
mm,
Actually,
mm.
we try to make a webinar about data center next month. I hope you
Yeah,
join that
yeah.
because Tensor HVAC is not only designed for building, for our architecture, it also used for data center. So the sorry, I forgot the question. I get too excited hearing. Okay, what to consider? So, first of all, again, simulation tool is just like calculator, garbage in, garbage out.
Mm,
No matter how you know good the brand of the software, or maybe the how advanced
okay.
the
Mm,
simulation. But if you input the wrong boundary conditions, of course the result will be garbage. But in Tensor HVAC Pro, we intentionally limits the flexibility of the user to select the turbulent model, to select some turbulent calculation, to just simply
mm.
input the velocity or input the temperature because of that problem. So we don't want the user to, get some uh uh get garbage input like wrong
Ah,
turbulent
okay,
model.
okay.
Yeah. So by inputting the velocity and the temperature, the software is doing its work to determine the turbulent calculation under the hood.
Mm.
So it minimizes the human error. That's the thing.
Oh,
Mhm.
okay,
That's
okay,
the
okay.
idea. Mm.
Mm.
But again, if you want to simulate is air conditioning system with, I don't know, Mach 1 velocity, of course the, the temperature will blow
Yeah,
up.
yeah.
Yeah, it's garbage in, garbage out. But yeah, we minimize that by using straightforward inputs. I have that's answer. I forget actually the question. And that's the question.
Yeah, I mean like just more than just to make sure like the accurate 3D flow and thermal simulation to representing like a actual building condition to meet
Mm,
set like a comfort standard. I mean like how to be like we make sure for the accuracy like that.
mhm. Yeah, that's actually a good question because in computational fluid dynamics, not only in TensorFlow, yeah, but
Mm-hmm. Mm.
in general, we actually use different methods to not only validate but also verify the result. So
Yeah.
if we have the existing building, uh, we can easily validate the data based on the existing data. Let's say the temperature
Oh,
distribution and pressure distribution. That's one thing. So that's validation can be used to like to change the variation or the placement to
okay.
get the
Okay.
exact value. That's the first one. The second one is if we just want to know the trend. Let's say if we put the blower in 100 or 200 or 300, how it will affect? It will be linearly change or put different trend. We don't have
Mm,
to validate that actually. We just want to show the trend. Yeah, that's the
okay.
another problem. So it depends on the application, whether you want to have uh like uh, exact value of the data, or you just to validate the trend. That will be different. Yeah, that's actually a very interesting topic in CFD, the validation and
Yeah, yeah.
verification.
I got it.
Mhm.
Maybe the next future, I can waiting for you to webinar for the especially for data center part.
Yeah.
That's very
Actually,
interesting.
I plan to do that because it
Mm.
is a huge topic lately.
Okay, okay, I got it.
And Tensor SVC definitely can do that.
Okay,
Okay,
okay.
another
Thank you
question
for
maybe?
answer.
Sure, thank you. Another question. Okay, I think we don't have many more questions. So thank you for joining for this very exciting topics. And I hope I can meet you again in the next session in the next year. Actually, it is already at the end of this year. So happy New Year, everyone, and happy holiday. Thank you for joining. Bye.